let's move to the next topic, which is Brewster's angle. Okay, so Brewster's angle happens only for a very specific polarization. So it is parallel or TM. Okay, so if you go back to the time instant where I showed the reflected and transmitted powers, right, for the two kinds of polarization, there was only one particular polarization that showed zero reflection, right, at some particular incident angle. So let us find out where this happens, right. So let us recall that gamma parallel, if it had to be 0, it implied that my eta 1 cos theta I was equal to eta 2 cos theta t, right, and I am going to already call the theta I, the solution for theta I where this reflection goes to 0, as theta b, or the Brewster's angle. Okay. And the other relation we have, so if I were to change this to index, right, what do I get? So eta, or the wave impedance, is inversely proportional to the index, right. So I have n2 cos theta b is equal to n1 cos theta t, and from Snell's law we have n1 sin theta b is equal to n2 sin theta t. Okay, so we are looking for the solution for theta b, right, that satisfies this particular pair of relations, right. Remember, one comes from the phase matching condition and the other comes from the Fresnel's relations, right. So if I were to multiply these two, I essentially get n1 n2 sin theta b cos theta b is equal to n1 n2 sin theta t cos theta t. So I can cancel off the product n1 n2, and I can say that sine of 2 theta b is sine of 2 theta t. Okay, so obviously the trivial solution is that theta b is equal to theta t, right, which means that there is no refraction happening, right, and the two media are the same. So we'll neglect that. That's obviously not true, because when you have two media that have the same permittivity, there's no boundary anymore, right. But there is a second way in which this relation can be satisfied, which is if 2 theta b were 2 pi minus 2 theta t, right. Remember, the sinusoid is positive in the second quadrant, right. So this gives us a relation that theta b is pi over 2 minus theta t. Okay, so this is very interesting. So this says that the Brewster's angle plus the refracted angle is 90 degrees. Okay, so basically if I were to draw this pictorially, so we have theta b, and this is theta b also, and we have theta t, right, and if theta b plus theta d is pi by 2, this angle is 90 degrees, right. So the Brewster's angle occurs when the angle between the reflected beam and the transmitted beam is perpendicular to each other, right? Alright, so let us take these two equations again, right? This has only got us the relation between theta b and theta t. It's not really telling us what is theta b, right? We need theta b in terms of known parameters, right? So only depending on n1 and n2, right? Or eta 1 and eta 2, if you will. Okay. So if I were to divide 1 by 2, right? So I essentially, or I should say, let's divide 2 by 1. Okay. I get n1 by n2 tan theta b is equal to n2 by n1 tan theta t, right? But we know something about theta t in terms of theta b, right? So theta t is just 90 minus theta b. Okay, so this implies tan squared theta b is n2 by n1 whole square, or theta b is tan inverse n2 by n1. Okay, you may have come across this relation also, you have even memorized it during the time of your high school, but now you understand where this comes from, right? So it essentially comes from the Fresnel's relations and Snell's law when combined to actually ensure that the reflection coefficient becomes 0, and we know that this can only happen with the parallel polarization given a non-magnetic media, right? So remember that this is the underlying assumption for all of what you are seeing here, right? Even the Snell's law in the form n1 sin theta I is equal to n2 sin theta t is all assuming that we have non-magnetic media, okay? But this should not bother you much in the sense that even if situations were to arise where you have magnetic media, you can always rely on the boundary conditions and go back to the original Fresnel's relations with wave impedances, which has the dependence on the permeability, right? So you can always incorporate it and get the appropriate relations, right? But the reason to choose a non-magnetic media is we can derive some of the relations that are probably more popular, right? But it also gives you context and how these are derived and how these relations came out to be. Okay, so one very interesting insight, right, on this Brewster's angle is I have personally been very fascinated that what is happening at this very special angle, okay, and how is it that this reflected light is completely removed, right? At least in the case of the layered media and the normal incidence case that we discussed with the soap bubble and the quarter wave transformer, I could talk about multiple bounces and the contribution at steady state coming from several interactions with multiple boundaries, right? And these having opposite signs can add or subtract with each other, and that I can see the cancellation, right? So there was a logic behind it. But Brewster's angle is one where I only have one interface, right? But yet I am able to completely cancel a particular beam, right? So there's no question of a destructive interference here, right? So remember, the incident beam is still there, right? It's not a question of the incident beam and the reflected beam sort of combining with each other and creating zero reflection, right? That is not what we are saying. We are actually saying that at Brewster's angle, the light fails to reflect, right, or we don't see any reflection coming off of the boundary, right. So it was fascinating when I discovered that this requires an atomic scale view, right, to actually understand what is happening at this very special angle. Okay. So remember that for pure dielectrics, right, is what we were discussing, and we are looking at the parallel polarization, which is the electric field is oriented this way, right. So we have a linear polarization where the electric field is essentially in the plane of incidence, right, this way. This is the only polarization that seems to have a Brewster's angle for non-magnetic media interfaces. So what happens to the electric fields after they reflect? They essentially are oscillating in these directions. Okay. So the first clue comes from the fact that this angle between the reflected and transmitted beam is 90 degrees, right. So the formation of the fields, right, in a dielectric media, I told you, is a very complex phenomena, right. So there is an incident field, but this media is filled with atoms or molecules that all have charges in them, right. So the nucleus has protons and the electrons that are spinning around it. They are all charged particles. So when I have an electromagnetic field, these fields obviously interact with these charges. So when I have a rapidly oscillating electromagnetic wave coming and interacting inside a medium, I essentially am perturbing the electrons and in the medium, that is essentially responding to this electromagnetic wave, and they are creating their own electromagnetic waves. Right? So each of the individual constituents of the medium, say the atoms or molecules or whatever be the unit cell, is essentially having free electrons that all vibrate or oscillate at the same rate at which the electromagnetic frequency that's impeding it. And these electrons that are jiggling inside each of these atoms are themselves causing electromagnetic waves, right. Now, the propagation of electromagnetic waves inside the medium is essentially the sum total of the original incident wave and the responses that are coming from each of the atoms of the media, right. If we had to really solve this as a problem with collection of accelerated charges, we don't have a prayer to even solve this, right, because we have Avogadro numbers of atoms and molecules, right. But nonetheless, we are able to simplify and say that the response of a plane wave just in a medium is by just assuming a permittivity, right, a scaling factor to the permittivity of the medium, and that was able to encompass it. But nonetheless, you should always have this picture in mind that when an electromagnetic wave is propagating in a medium, it's actually exciting the free charges that are not quite free charges. These are charges that are circulating around the nucleus, right, each atom, and those electrons are all jiggling, right, in response to this electromagnetic wave, and those jiggling electrons are accelerated charges and they create electromagnetic waves of their own, right. And the net composition of all the electric fields from all of these accelerating charges within the medium is responsible for the net movement of the electromagnetic wave in the medium, right. But we also know that the electron, right, feels a pull or a push in the direction of the electric field, right. So if the electric field is oscillating one way, we expect that the electrons are moving in response in the same direction, right, which means to say that we set up tiny dipoles, right, where the axis of the dipole, right, that is these electron clouds slightly separating off from their nucleus and creating momentary positive and negative centers within the atom, create a small dipole moment, right. And this dipole moment, the axis of this dipole moment is essentially lining up with the electric field, axis of the electric field, right, along the polarization. So I expect tiny dipoles, right? So this is an atomistic view, right? I am looking at each and every individual atom, and it will basically have these electron clouds that are sloshing back and forth, and while they do so, they create momentary dipole moments, right? But the axis of these dipole moments will be in the same direction as the oscillation of the electric field, right? So the electric field vector is linearly polarized, and it defines a certain axis, and all the dipole moment axes are aligned up with that. And for keen readers, the emission of electromagnetic waves around a point dipole, such as these atomic dipoles in a media, has a certain radiation pattern, right? Okay. So this is normally covered at the introduction for antennas, right? So small accelerated charges coming from a point dipole has a radiation pattern which essentially says that along the dipole axis, the amount of electromagnetic wave strength, right, that is being emitted by this point dipole is close to 0, right. It actually follows a sign expression with theta, right. So this angle is theta, the power radiated is a function of sine theta. So you can see that as I look at the direction along the dipole, right, I basically have no emissions, right, no radiations. So even though these charges are accelerating within the media too, it so happens that at this special angle, when the reflected beam and the transmitted beam are 90 degrees to each other, that all the dipole moments in medium 2 are lined up in a fashion that the axis of this dipole moment is lining up with the direction of the expected reflected beam, right. And since all of these radiating dipoles are not radiating in the direction of the dipole moment, we expect to see very little to no radiation coming in along this axis, right. So this is a very interesting insight to understand how that we are able to get zero reflection with a single boundary, right. This is what makes Brewster's angle special, right. So we have these Avogadro number of atomic dipoles, but they all seem to be lining up themselves such that in the direction of the expected reflected beam, there is no emission from these dipoles. So it is to not say that there are no oscillating electrons or oscillating charges, but it so happens that they are all lined up very precisely so that the reflection is completely non-existent, right. So it is not really a cancellation process, but instead it is non-emission of atomic dipoles from the second media. This also gives you clues to seeing how the reflected beam is actually formed, right, which means to say that for other angles other than Brewster's angle, the fact that there exists a reflected beam is actually sourced by the individual dipole oscillations that are in medium 2, right. So it is also a fascinating insight in that sense. Alright, so now we will move to total internal reflection.